Greetings, everyone. I am Maxwell Fox, a student at University of Alabama in Huntsville, and over the summer of 2020, I have been working with Dr. Shangbing I and Dr. Mark Pekker of the UAH Department of Sciences on a project we have entitled A Mosquito Population Model with 4 Positive Equilibrium Points and Sterile Insect Release. So let's get right to it. Alright, so throughout history, mosquitoes have been not only a nuisance, but a persistent disease vector for all sorts of deadly diseases across the globe. Because of this, controlling their populations has been a much discussed topic in academic research. One method that has been used to control mosquito populations is the sterile insect technique, which uses lab-created sterilized insects to disrupt the populations by having wild mosquitoes breed with sterile mosquitoes in order to reduce the birth rate significantly. So to determine the efficiency and effectiveness of certain release rates, various mathematical models have been developed to to ascertain the efficiency and effectiveness of various release rates. So over the summer, we have been studying a specific model for a specific type of release rate. So, as seen here, if we let the wild mosquito population be W of T and G of T denote the sterile population, then we describe the dynamical system that has been described by Kai and researchers, including Dr. I, is as follows, where mu1 and where the mu1 and mu2 are density independent death rates, which essentially correspond to the lifespan of the mosquitoes, and Z1 and Z2 are the density dependent death rates, essentially dependent on, which is here a proportional to the total population. And here we have a release rate B of T is equal to B times W over 1 plus W. It is roughly, it's a release rate that's roughly proportional to the wild population, but approaches a constant B as the population grows larger. As you can see, all the values listed here are positive. So when understanding the long-term behavior of systems such as these, it is critical to know the equilibrium points, or the points where the derivative is 0 for all t of the system. It's been previously shown that if by a team of researchers, including Dr. I, that if mu1 equals mu2 and z1 equals z2, then the system 1 has only 2 positive equilibrium points, that is, points in the where both W and G are positive. Another team of researchers argued that this result, that only 2 positive equilibria, would always hold for any positive values of coefficients. However, we have discovered some counterexamples to this claim over this summer. As seen here, we have case 1 and case 2 have been labeled. If the parameters equal these values, then it can be shown that the system will have 4 positive equilibrium points. And it's worth mentioning that if in the second case, if we let mu1 equals 0, then we will have 3 equilibrium points. And it's important to note as an interesting biological ramification that in both of these cases, and in fact all the mu1 is less than mu2, which implies that wild mosquitoes have longer lives than their sterile counterparts. So for these parameters, we can verify the number of equilibria using a technique similar to that of Kai, I, and Lee. If we perform a substitution, n equals W plus G, Then after some algebra, we can show that W and G are uniquely determined by the equations shown here for W and G essentially. Furthermore, we can also show that the equilibria are determined by the zeros of this fifth order polynomial displayed here. For case 1, the polynomial described in 2 becomes the following polynomial. As you can see, it's easy to see here that for n equals 0, this is greater than 0, and after some computation, we'll show that we have a variety of values of n that guarantee that, for instance, around 0.85 is less than 0. At n 4.4, p is greater than 0, but at n equals 15, p is less than 0. We also know that p of n has a positive leading coefficient, meaning it must tend toward positive infinity as t goes to infinity. So from this we can deduce that it must essentially cross the n-axis at least four times, and thus it will have by the intermediate value theorem, it'll have 4 zeros. We can make a similar argument for case 2 using the n values described here for a p of n, with this determined by the coefficients as in case 2. All right, so here are some graphs of the system with the coefficients of case 1. In case 2, the equilibrium points are different, but the overall general dynamics are similar. So I'd like to direct your attention here to figure 1, and circled here in dark blue are the saddle points of the system. This is where, for most cases, for most initial conditions, rather, the solutions to this system of equations will tend away from these points. And in cyan, we have these unstable separatrix, and for green, we have the stable separatrix for each of the saddle points, which are together these determine where the equations will tend toward the system, and will tend toward. And here, circled in black, are the stable equilibria points, including the 0, as in extinction of the population, and as we see two other stable points where the mosquito populations remain at a constant. So in all, there are 3 possible values for which the mosquito population can tend toward, depending on the initial conditions. Now, in the 2 equilibria case, there's only 2 of them, but in this case, there can be 3 possible places for the mosquito population to end up, which has significant ramifications for the overall population dynamics, of course. And in figure 2, we have a close-up view of the stable point 0, 0, and the saddle node 0, this over here with us. So using case 1 as a starting point, we also performed a continuation of the equilibrium curve, or by varying mu1, meaning that we analyzed a curve, the curve of one of the equilibrium points as mu1 was altered. This was done with the MATLAB package CL-MATCONT-L, which was developed in part by Dr. Pekker himself. So our analysis found that mu1 undergoes a saddle node bifurcation, meaning to one of the saddle nodes one of the stable points sort of collapse into each other and form a single point at around about the value approximated here. And also it suggests that for mu1 greater than this value, if all the other coefficients are kept as in case 1, we go back to having at most 2 positive equilibria points. So in conclusion, we have verified and discovered and verified that this system described here can have up to 4 positive equilibrium points, and since then these equilibria can predict the long-term population behavior with this model, the knowledge of these equilibria is very important. So we hope that future research can elaborate on what coefficients are needed to guarantee more than 2 positive equilibrium points. So here are the references mentioned in these slides. Thank you for listening, and I hope you have a good day.